In this demonstration, I will show you how to describe thermal diffusion by coupling a steady-state thermal system that uses the mechanical solver with fluent using system coupling. The case involves a heating coil immersed in a flow of water contained in a pipe. I want to determine the temperature distribution of the heating coil and the flowing fluid. To do this, I need a steady-state thermal system to describe the temperature of the solid coil. I need a fluid flow system that uses the fluent solver to describe the temperature of the moving fluid. As well, I need system coupling to transfer temperature data from the mechanical system to the fluid system. The external data system facilitates the transfer of data from mechanical to the fluent solver. Note that this is a one-way data transfer method. Temperature data will only be transferred from mechanical to fluent. The fluid flow and thermal simulations have been set up. For this demonstration, I will review the settings pertaining to a coupled analysis in each system. In the thermal system setup, we can see that only the coil has been meshed. The container geometry has been suppressed. The initial temperature of the coil has been set to 250 degrees Celsius. This will be the coil's temperature during the first iteration of the mechanical solver. The heating in the coil will be generated internally through the application of a constant power. The convection boundary condition is applied to the outer coil surface, not to the ends. The heat that is introduced by the internal heat generation setting is dissipated due to convection. In the analysis settings, the simulation was set to have a single step. This means that within each coupling iteration, the mechanical system will calculate one step and then transfer the solution data to system coupling. The fluid-facing surface of the coil was set as a fluid-solid interface. On this interface, mechanical exports temperature data in the form of a .axdt file, which will act as an external data source for the one-way coupling setup. To facilitate the transfer of data from the .axdt file, I must specify its location in the external data system. The file can be found in the cases directory. The mechanical portion of the setup has been reviewed. Now I will review the fluent setup. As we can see, the mesh for the entire assembly is present. I have set a velocity inlet and a pressure outlet. The working fluid for this case is water. The coil surface is set as a wall boundary. Its heat transfer option is set to system coupling. This allows fluent to receive temperature data at this boundary from system coupling. I have set the solver to use the pressure velocity coupling method. This simulation will run for a maximum of 200 iterations or until the shown convergence criteria are met. Now I can close Fluent and update the components upstream of system coupling. In system coupling, I will keep the default analysis settings for this run. A maximum of 5 coupling iterations will be performed. I will set up the temperature data transfer by selecting the file region, right-clicking the temperature output, and selecting Create Transfer. This sets the external data file as the source for the created data transfer. The recipient, or target, of the data transfer must be set. The participant is the fluid flow system that uses the fluent solver. The region is the coil surface. The variable is temperature. The data transfer is ready to relay temperature data generated by mechanical to the fluent solver at the beginning of each coupling iteration. I will start the calculation by updating the solution cell. The data transfer has converged and the solution is ready for post-processing. I can analyze the solution in CFD Post by linking the solution cell to a single results system. Using CFD Post, I generated this temperature contour plot showing the temperature of the passing fluid and the heating coil. This concludes this demonstration, showing you how to use one-way system coupling to describe the temperature of a flowing fluid in a pipe with a submerged heating coil.